first of all, I would like to thank the organizers for such a nice idea to collect so many different topics, but still interesting and somehow also everybody can understand anything. And I promise also mathematics will become now not complicated. And I would like to thank Christian Deppe for inviting me to participate this conference. Okay, cryptography meets mathematics. My problems usually are motivated from symmetric cryptography. And when we consider symmetric cryptography, and now it doesn't work. Oh, yes. So we have the same key for encryption and decryption. Plain text to ciphertext, it means that we have, in the case of binary alphabet and block ciphers, we have a function which maps some vector of length n to something again of length n binary, and what is going here that we inverse the same function. So, and this is the motivation what we are doing. Okay, but in my group we are considering very often mappings from finite vector spaces and which are also bijections. Okay, and when we have cryptographic mappings, then what we want to have two properties. Our mapping must be secure and it must be also practicable. It means that we want to have secure and low implementation costs. When we think about security, it means that our function must be complex. And when we work with F2 to the n, so it means that everything which, every map can be represented as a univariate or multivariate polynomial. It means that I can use a vocabulary for polynomials to say what I think about security. So it means that intuition would say we need to have large degrees. We must have many non-zero terms in our polynomials, and also we need to care about nonlinearity, which needs to be defined. And this is not the topic for this talk. And then implementation, they just reverse everything what was above. So we want to have small degree, we want few non-zero terms, and so on. Okay, we have two contradictory properties, and the answer, how can we achieve this, came already from Claude Shannon. He said, take simple maps and iterate them. So this is how many cryptographic protocols work. They just take some function and then iterate them with linear function and again the same function and so on. And there are some functions which are quite famous in symmetric cryptography. One of them is the so-called he-map. It was introduced by Johan Damon in his PhD thesis, and after that was used in many of known cipher. So SHA-3 is the standard for hashing, and the others are encryption style. I guess. So, okay, this is just to do some Werbung, advertisement. It is known that Johan Damon is very fond of this function he, and this is what you can read on his homepage about he. This is the simplest nonlinear shift invariant I will define in a few minutes. So this is the simplest nonlinear shift invariant mapping that is invertible. So then comes something, and I cannot think of another nonlinear mapping that comes close. And the only disadvantage is that it is not invertible for n even. So these things we will see today, how we can find something which comes close to she, which is invertible for n even and also shift invariant. Okay, Now, what is He function? He function is defined as follows. We have a vector of length n. It will be mapped to vector y. And the way we do it, we just described every coordinate yi. It is just xi plus this term. And indices are taken modulo n. So the way how Damon is thinking about this function is in combinatorial way. He says that if we want to have that xy is changed after applying He function, it means that I want that xi becomes xi plus 1. It can happen only if the second summand is 1, and this will happen even only if xi plus 2 is 1 and this 1 is 0. Okay, so and this is the way how he describes. He flips the bit xi if and only if xi is followed by 0, 1. So combinatorial definition, in his PhD thesis, he showed that He is a permutation if and only if n is odd. And this was done in a way that he described just by an algorithm how you invert He function. So he gives a way how we can find the inverse function of He. What is shift invariant? We will speak, as I promised, later about that. And there is another paper from 2023 which gives a formula for inverse of He. Again, this is a proof that then He is a permutation. If you have a inverse function, then it is bijective. Good. Why we started to think about He? This was this conjecture by Damon and his student. I forget the name. Okay, so I guess I will not say. So there was a conjecture about 20 gain 3 that if we can take now the formula for He function and try to understand what happens if we work not over F2 but over any field FQ. And the conjecture was that this will be a permutation only if Q is 2. There were some attempts to prove this conjecture by very complicated tools from Grobner basis methods and so on. What we did, we proved this conjecture by simple linear algebra methods. But working on this conjecture, I was always thinking about this sentence. If you can find inverse of a permutation, there must be a nice property which allows that, because in general, for generic permutation, you cannot expect that there will be a closed formula describing this inverse. But the problem with He is that it is defined as a periodic function. And if you start to think this combinatorial way, you have something which in combinatorics is carry. So, and this carry makes everything complicated. So, and I was about to give up this trial to find a nice property for He, why it is invertible, until I've seen this formula for, I show that formula soon. So we will use a new notation for He, which says, okay, we have two operations in our He function. One of them is cyclic shift. So we take something, x1, xn, and then cyclically shift it. And the second one, what we are doing is we multiply entries component-wise. So this is the Hadamard product, which says that take product of each position. And having this notation, I can write He in a very compact way, in this way. So it says take the identity map, take the map shift 2. So it means we apply shift twice. Then take all one vector, add one shift of x, and multiply this two stuff component-wise, a Hadamard product of it. So having such a formula, you can try now to play with iterates of here, and we did it. When we iterate here, then something which we called later gamma, and I will explain that, appeared in these iterations. So the first thing is just identity map. It will be called from now on gamma 0 function. Then we have gamma 2 and so on. What is gamma 2k? So gamma has always even index, and it says take the 2k shift of x. So multiply with such, then Hadamard product with such sums where always we have one vector, and we have shifts which are odd, starting with 1 to 2k minus 1. So 2k describes which products we need to take. So it means that gamma 2 will be, for example, S2 multiplied by 1 plus S1, and that's okay. So having gamma notation and these examples, we could conjecture that he is a linear combination of gamma functions. It looks like that. And if we somehow can prove that, the next question is, what is the general pattern of these iterations? So which linear combinations of gamma appear? So the good news is that not, so we defined gamma functions for infinitely many k, but only finitely many of them are not zero. So starting when 2k becomes larger than n, then we have zero function. And it means that when we iterate here, then we will not have very complicated formula. They will start somehow to repeat. And why this happens, now I need that n is odd. Remember, he was bijective only when n was odd. And we need that n is odd because if 2k becomes larger than n, S is shift. If we shift n times, then we return to the same vector we had at the beginning. So it means that here I will have 2k minus n, n is odd. So I have here now an odd S, odd shift. But all shifts, we have here saturated product. So all odd shifts appear in one of these parentheses. It means that I will multiply S with complement of it. It means that in any position we will get zero. And this is something which will help us to get our results. Another thing which we can see is that if we have in a linear combination of gammas, gamma 0, the identity map, and then we take composition. So now I start to work with composition. Iteration means that we will take here and iterate it. So, and we take the composition with another gamma, then we are again a linear combination of gammas. Again, interestingly, this is not true if gamma 0 is not involved. For example, if we take gamma 2 composition with gamma 2, it is not anymore linear combination of gammas. And this formula says even more, you know which linear combination we are getting. So it is just 2i plus 2m. So you shift every gamma by 2m. Okay, so, and okay, at that point, after seeing this, we tried to understand iterates of Xi and were not so successful. And then Bjorn Kripke, who is co-author of this paper and my PhD student, he suggested to look on this set. So we take gamma 0, add to it all spans of gammas which we are working with, and consider this coset of vector space spanned by gammas. Okay, so our he function is there. Also the identity map is there. We have our key lemma, which says that if you compose with gamma 0 involved, you will stay in the set of spans of gammas. It means for this set gamma that it is closed under composition. So key lemma says that we have gamma closed under compositions. Identity map is there. It means that in fact we have a monoid. So because composition of maps is associative, so we have algebraic structure. Yeah, you could wonder why it is so interesting. Because if you again look on these formulas and try to understand what is going on, it takes a few days or sometimes weeks, but still then you have something in mind. It reminds us of something. So this looks like something we all know very well. Yes, we know it. It looks like polynomial multiplication. You see, I add here to 0 to 2 and so on. So it is polynomial multiplication what we have here. Okay, but we need to take the correct way of polynomials, because remember, when n is too large, then we have 0 maps. And this is again something you can translate to polynomial language. It says that you need to work modulo this polynomial. So we are not in the polynomial ring, but in the quotient ring of this ideal. Okay, so this parenthesis, they say just that we take always coset of the polynomial modulo this ideal. It means that just we need to remember that we are working with a remainder when we divide our polynomial by this one. So this is what the message here. Okay. And now it starts to be interesting. If we take the set G, this was the one where gamma 0 was present, which was closed under composition, and take, after translating it to the polynomial language, take its image, then it is the set M. One means that we have gamma 0 in our set G. Okay, and this is a nice subset of the ring, of polynomial ring modulo x to the power something. Therefore, I can, so it is easy to see that M is closed under multiplication in that ring, because 1 multiplied with 1 will stay 1. Yeah? And then because we work with polynomials, so we have 2, it is also abelian. M is an abelian monoid. And phi map, which I described before, so this translation of gamma function to polynomial form, is an isomorphism, monoid isomorphism. And this means that I have for free now that G is an abelian monoid. It is rather rare property for mappings that you have commuting mappings. Yeah, so we have now a commuting mappings. It is a kind of miracle. But it becomes even better. M is a group. It is not only monoid, it is a group. And it means that my G is also a group. Again, for free, I get something proved which is not so easy. I showed that any map here is a permutation. Okay, and not only permutation, it is also commuting. Okay, so this was something we were very proud about. And what allows this theorem? any G which we take from this simple set, now it is simple, has the property that if you compose G with S, then so the map commutes with shift. It is exactly what shift invariant is. So I promised to explain what does it mean. So G is a permutation. Okay, now she was special. We could describe its inverse. And this is again here. If you work with polynomials in some rings, then describing inverse means that you can do it with help of extended Euclidean algorithm. So I have also this tool now and I can use it. And also there are some observations which will allow us to speak about degrees of these two maps, which are again for cryptography interesting parameters. So having permutations which have one of these properties is already very rare property. And now we can guarantee many of them together. And this is something unusual. Okay, and now again, returning to Xi. If I take its polynomial representation, then it is just 1 plus x. And looking for its iterates, it means I need to understand what is going with 1 plus x to the power k in the ring where I'm working. And then we can use two standard things, binomial theorem and Lucas theorem about parity of binomial coefficients, and have such a nice formula for the iterates of Xi. Okay, what this thing means is not so important now. Another interesting thing is that, remember, Damon was complaining about an even case. And for an even case, some of our identities I showed will not work. But we can again consider this span or coset of span of gammas for n even, and do some, again, the similar steps, and they lead to the fact that now we are working modulo this polynomial xn plus xn half. This polynomial is more interesting for mathematicians. This is, in fact, what we are trying to understand here, the cyclotomic polynomial, and there are many results about it. But again, this translation allows to construct polynomials with properties required in cryptography. Okay, so the papers which I used for my talk are for n odd, this algebraic structure of the iterates of Xi. For n even, we have a submission, and there are siblings of Xi which are permutation for n even. And there is an application of our methods to define other formula, which will again guarantee that you have shift invariant permutations with properties you can control. What now Bjorn is doing, he is trying to classify all formulas you can reduce to polynomials. So this is what probably in 1 year will be done. Okay, thank you very much.
Yes, thank you for the talk. Are there questions? Okay, thanks a lot. So the you found a lot of algebraic structures in this mapping, so much that it is that the, you might comment on the cryptographic implications that it has, because it says basically the way how you invert composition. Does it work here? Anyway, so the right. So what does it mean for the cryptographic application of these functions? Probably a lot, right?
Okay, you see, the first paper was accepted for crypto, and it means that exactly that issue was raised there. Somehow there were 3 referee reports, and all of them tried to understand why it is not so bad for cryptography, for the applications. And I agree with them that it is not bad, but it needs to be understood. But it is not bad because for IES, you use the function 1 over x, which is again very easy function. So you just take the inverse function 1 over x, but after you compose it with linear functions, and linear function destroy all properties which you have in this inverse function. And the same happens in the applications with He. You don't apply He without, so in pure way, but you compose it step by step with linear functions. And this is what seems to be responsible for complication, so for that it will remain complicated. So yes, but so degree is, so if I understand the question correctly, degree is, for example, for He, 2, where is it? Yeah, no, not here. You see, the degree, multivariate degree of He function is 2 because all coordinate function of it have a term extreme times x2 and so on. So it means that multivariate degree is 2. And yeah, and if you compose now this small function with the linear functions, then they will become more and more complicated. So sparse means that you have a few terms in the description. And if you do it with linear functions, iterate with linear functions, you lose this property. So is it what you okay?
I understood you attack AES, etc. So you write these, huge equations. So you have known plain texts, and then you write, the equations up, and then you try to see, okay, what is the degree and what is the sparsity, and then you're trying some solver, even a quantum solver that solves these multivariate equations which are exponential in size, right? But if you know all these structure, I think this can has severe implications how to solve this.
I hope, or maybe not. I don't know. Should I hope?
So we haven't found. Okay, that's good.
No, we asked all. So we were also on Eurocrypt with this talk, and we asked the practical computer scientists. Maybe they can. They have some problems which we can help to consider, but they avoid us. So.
Is there another question?
In fact, what is more dangerous is that with more applications of He, you become too near to the identity map. So because if you have this, this function, it has very few non-zero terms. So it means that after several applications of He, almost everything will become a fixed point. This is the main danger, I guess.
Thank you for your interesting talk. I have a simple question because if I understand, you have 2 functions, and gamma function is the linear, and Xi function is the non-linear.
Gamma is non-linear. It's highly non-linear.
Yes, yes. My question: if we have a group, because you define a group with based on some probably additive or multiplicative operator. And my question is about, did you have an operator? Because if we have the algebra structure, we can change the from the polynomial form, and we can find isomorphic operator. For example, we have some car algebra or something algebra.
Yes, this is what in this paper is done. So they changed somehow these gamma functions, which were based for our consideration, to something which they call theta, and they do similar stuff. And what is now Bjorn doing is also the same. When you can do this change, when it is going to work, and it's interesting question. It's not easy to answer. And remember, it is not so easy as it seems, because it is not very, I map my gamma to X, yeah? But I said, where it is, if you take two gammas and multiply, it is not anymore something in this group G. So it is not very easy. I don't understand. I accept it works. I know the proofs are correct, but there is something which is yet not clear to me. And this is why it works.
Okay, thank you very much.
Yeah, thank you and all the other speakers again.